Good morning, students, and welcome to the next part of the lecture series on solids. In today's class, we will discuss about the different laws of crystallography. Crystallography is a branch of science that deals with the study of geometry, properties, and structure of crystals and the crystalline substances. The three fundamental laws of crystallography are law of symmetry, law of constancy of interfacial angles, and law of rationality of indices. Coming to the first law of crystallography, the law of symmetry, most of which we have already discussed in our previous lecture. We know that crystalline solids have a very regular and ordered arrangement of constituent particles. The geometrical regularity that arises due to this ordered arrangement is what is referred to as symmetry. And the symmetry in crystals are based on the unit cell parameters, and we have already seen what are the unit cell parameters for the different crystal systems. There were 7 crystal systems which we have already studied and which had varying edge dimensions A, B, and C, and the angles between them, that is alpha, beta, and gamma. Crystals can have one or more types of symmetry, and all crystals of the same substance will have the same symmetry elements. Say for example, if we take sodium chloride, a sample of sodium chloride, whatever number of crystals are there in sodium chloride sample, all the crystals, each and every crystal will have the same symmetry elements. Symmetry elements, we have discussed about them in details in our previous lecture. We have understood what plane of symmetry is, what axis of symmetry is, and what is the center of symmetry with reference to a cubic unit cell. So the law of symmetry encompasses the symmetry elements and the symmetry operations performed on the crystals. So in this lecture, we'll basically focus on the remaining 2 laws. Coming to the second law, the law of constancy of interfacial angles. Before we understand this law, let us first of all see what is the meaning of an interfacial angle. As you can see in front of you on screen is a quartz crystal. And it's a mineral. Quartz is a mineral, you know, and there are 4 faces clearly shown in this on the surface of this crystal, 1, 2, 3, and 4. And if you see it clearly, there will be a sharp bend between the faces. That means there is a certain angle, there is a definite angle in between the 2 faces of this quartz crystal. Now there are 2 more crystals shown here on screen. You can see this is a big size crystal while this is a smaller one, and the shapes are also different. The angle between any 2 faces on the surface of the crystal is called an interfacial angle. Like the angle between this face 1, as you can see here, and the face 3 here. The angle made between 1 and 3, this angle is called an interfacial angle. Similarly, between 1 and 4, the angle between these 2 faces is the interfacial angle. Similarly, between 2 and 3, the angle between 2 and 3 is an interfacial angle. Now, what this law states that no matter whatever the shape and size of the crystal is, the interfacial angles will always be equal. As is clear from these 2 pictures, both are quartz crystals, but this one is smaller in size as well as a little bit distorted in shape also. But this one is perfectly shaped and bigger in size. Size and shape of crystals depends upon the conditions applied during crystallization process. But it doesn't affect the interfacial angles. Interfacial angles, irrespective of the shape and size of the crystal and the conditions of crystallization process, are always equal. So you can see in both these crystals of quartz, the interfacial angles are 120 degree. Hence, this law states that the interfacial angles in crystals are always equal. Coming to the next law, the law of rational indices. Before we dwell in deep into this law, let us first of all understand the concept of crystallographic axis and a unit plane. Here in front of you on screen is a unit cell, which we had discussed in details in our previous lectures. A unit cell can be represented with the help of a coordinate axis x, y, and z, and the edge dimensions a, b, and c, and the angles between the edges, that is alpha, beta, and gamma. Now in a unit cell, if we cut out a plane out of this unit cell, this triangular plane, as you can see, A, B, C. Suppose we cut out a plane from this unit cell, then the intercepts of this plane will first of all be regarded as a unit plane because it has been cut out of a unit cell. So this plane ABC is a unit plane. Now this unit plane is making an intercept on the x-axis, as you can see at this point A. So the intercept made by this unit plane ABC on the axis x is A, small a, as represented here. Similarly, this face is also making an intercept on the y-axis, and this is equal to b, small b. Also, it is making an intercept on the z-axis, so this intercept is small c. These are the unit plane intercepts, while the axes x, y, and z are the crystallographic axes. To understand the law of rational indices, let us first of all consider a unit plane ABC. Now this unit plane ABC is a part of the unit cell. The intercept made by this unit plane ABC along the x-axis is A, along the y-axis it is B, and along the z-axis it is C. So we can represent these intercepts as OA equals to A, OB equals to B, and OC equals to C. So this is along the x-axis, this is along the y-axis, and C along the z-axis. So these are the unit plane intercepts along the x, y, and z-axis respectively. Now let us consider another plane, and this time it is a crystal plane PQR. This crystal plane PQR also makes some intercept on the x-axis, on the y-axis, as well as on the z-axis. And the condition for these intercepts as prescribed by the law of rational indices is that these intercepts may be equal to the unit plane intercept or they may not be equal to the unit plane intercepts. If they are not equal to the unit plane intercepts, then there must be some simple whole number multiples of the intercepts of the unit plane. So now let us consider that this plane PQR makes the intercept OP along the x-axis. Suppose it is equal to small p, and this is equal to some whole number multiple of the unit plane intercept A, that is n times of A, and this is along the x-axis. Similarly, along the y-axis, the intercept is OQ. Let it be equal to small q, and it be equal to n prime times of the intercept made by the unit plane ABC along the y-axis. Next, let the intercept made by this plane PQR along the z-axis be OR, and that is equal to r, small r, and that is n double prime times of the intercept made by the unit plane C along the z-axis. So altogether we have got a set of intercepts for the PQR crystal plane and for the ABC unit plane. Now, the law of rational indices states that the ratio of these intercepts, that is OP by OA, intercept made by the crystal plane PQR, the ratio of the intercept made by the crystal plane PQR to the intercept made by the unit plane ABC along the three axes may be written as OP by OA is to OQ by OB is to OR by OC, or we may write this as P by A is to Q by B is to R by C, and that is equal to the coefficients of the intercepts, that is n, n prime and n double prime. The ratios between n is to n prime is to n double prime. Here the coefficients of the intercepts made by the crystal plane PQR is actually represented within parentheses as n, n prime, n double prime, and this represents the crystal face PQR, and this kind of representation is termed as Weiss indices. So any crystal plane PQR can be represented by Weiss indices, that is n, n prime, n double prime. What are these n, n prime and n double prime? They are the coefficients of the intercepts made by the unit plane, that is A, B and C. And these are actually whole numbers. So the law of rational indices states that the intercepts which any plane of a crystal makes on the crystallographic axis may be either equal to the intercepts of the unit plane, or it may be some simple whole number multiples of the intercepts of the unit plane. But if some plane is parallel to one or two axes, then the intercept made by that plane will be considered to be infinity, and we'll discuss this shortly. So far we have come to understand what is law of rational indices and how a crystal plane can be represented with the help of Weiss indices. Now we will try to learn how we can write the Weiss indices for any crystal plane. For that, let us suppose that a crystal plane intercepts the x-axis at thrice the unit cell intercept. Consider the above diagram that we had discussed. Suppose that OP here, OP is 3 times the intercept made by the unit cell intercept, that is 3 times of A. Similarly, suppose that OQ, that is intercept made by the crystal plane on the y-axis, is 2 times the intercept made by the unit plane, that is B, 2 times of B, and the intercept made by the crystal plane, that is PQR, along the z-axis, let us suppose it to be twice the intercept made by the unit plane ABC. So if this is the case, then we can write now that OP, which is P, will be 3 times the intercept made by the unit plane ABC on x-axis. Similarly, OQ, which is Q, is 2 times the intercept made by the unit plane, that is B, along the y-axis. Similarly, the intercept made by the plane PQR along the z-axis is equal to R, and suppose it is 2 times the intercept made by the unit plane on the z-axis, that is 2C. So how do we write the Weiss indices for this plane PQR? How to represent this PQR plane with Weiss indices? For that, you just have to see the coefficients of these intercepts made along the 3 axes x, y and z. So what is the ratio of these intercepts? It is 3:2:2, and the Weiss indices will be simply written as 3, 2, 2 within parentheses, that is small braces. So this crystal face PQR can be represented by the Weiss indices 3, 2, 2. This is how we can use Weiss indices to represent any type of crystal plane. But let me tell you that the Weiss parameters are the ancestors of a new set of indices which was devised later on and which we'll discuss now, that is Miller indices. Although these wise indices, they give us an approximate indication of a phase orientation with respect to the crystallographic axis, but it is a better way to use the Miller indices, and it's the latest convention to use the Miller indices now to represent the crystal planes along the three crystallographic axes, that is X, Y, and Z. To understand how to write the Miller indices for any crystal plane, let us take an example continuing with the previous one. In the previous example, what we had seen that the crystal face or the crystal plane PQR was making intercepts 3A on the x-axis, 2B on the y-axis, and 2 times of the unit plane intercept 2C on the z-axis. And so the wise indices that we got for this crystal plane was 3, 2, 2. Now using these wise indices, we can find out the Miller indices for this crystal plane. So how do we do that? For that, the very first step is that we have to take the reciprocal of the ratio of these intercepts. So we have to take the reciprocal of the coefficients of these intercepts. So starting from the wise indices, that is the ratio was 3:2:2. Now take the reciprocal, that will be 1 by 3 is to 1 by 2 is to 1 by 2. Now because the denominators are different, so we take LCM of the denominators here, 3, 2, 2. So LCM of 3, 2, 2 will be 6. So we multiply this LCM, multiply all the coefficients by this LCM 6. What do we get? We get 2 is to 3 is to 3. Now after taking reciprocal and multiplying by the LCM, the new set of parameters that we got is 2 is to 3 is to 3. We represent these new parameters as 2, 3, 3 within parentheses, and this new set of parameters is called the Miller indices for the crystal plane. And this is how we deduce the Miller indices using the wise indices, or simply it can be calculated, it can be deduced directly from the intercepts, that is the coefficients of the intercepts made by the crystal plane. Now there are certain other things that we need to learn about the Miller indices. That is, suppose there is the unit plane that we had discussed earlier. A unit plane makes unit intercepts on the 3 axes. So the Miller indices for the unit plane will always be represented by 1, 1, 1. Suppose there is a crystal face which does not cut any of the crystallographic axis. Let us consider a plane which will not cut some axis at all. Like suppose here I am drawing one plane. As you can see, this plane cuts the x-axis but is parallel to the y-axis. If this is the x-axis and y and z-axis, then you can clearly see that it makes some intercept on the x-axis. That means there is some intercept A over here, but the plane is parallel to y-axis or z-axis, or we may say that it is not cutting the y and z-axis respectively. So in such a case, the intercept along the x-axis can be taken as, the unit intercept along the x-axis is 1. Along the y-axis it will be taken as infinity, whereas along the z-axis also it is taken as infinity. So the wise indices, if we try to write the wise indices, it will be 1, comma infinity, comma infinity. And what about the Miller indices? Miller indices are the reciprocals of the wise indices. So from this we can write the Miller indices to be reciprocal of 1 is here 1, for infinity it will be 0 and then 0. So the Miller indices for this plane will be 1, 0, 0. That is how we write the Miller indices for a plane which does not cut some of the axes. And for that the intercept must be taken to be infinity. Now that we have known how to write the White's indices and Miller indices for a crystal plane, let us summarize the Miller indices and define it. In short, the Miller indices are a set of integers HKL in parentheses which are used to describe a given plane in a crystal. You take any plane inside a crystal and you can define it using the Miller indices. Miller indices, as we have seen so far, they are the reciprocals of the coefficients of the intercepts made by a crystal plane on the crystallographic axis. So for example, if you say that a plane has a Miller indices 1, 1, 0, and it will mean that the plane intersects the x-axis and y-axis, but it is parallel to the z-axis. Let us now understand how we can write the Miller indices for the 6 faces of a cube. You may expect this kind of question in your examination. A cube, as we know, has 6 faces. That means 3 sets of opposite faces. Each face can be defined with a particular set of Miller indices. Here, for convenience and for the sake of distinguishing the 3 different set of faces here of the cube, we have color coded the cubic faces. The 3 sets of faces have been coded as pink, yellow, and green. Let us first of all see the Miller indices for the pink face. Pink face, as you can see, is clearly making an intercept on the x-axis. So the unit intercept made by it can be represented in the form of a Weiss indices, that is 1. And since this plane, this face, is parallel to the z-axis as well as y-axis, so the remaining 2 intercepts will be taken as infinity, because we know that according to the conventions, whenever a plane is parallel to a particular axis, the intercept is taken to be infinity. So the Weiss indices for this pink plane, pink face, is 1, infinity, infinity within parentheses, that is small brackets. Similarly, for the face opposite to this pink face, that is this face, if you can identify this face at the back side, this face, clearly this face is making an intercept on the negative x coordinate, negative x axis. So obviously the intercept will be negative, the unit intercept here, because we are considering a unit cubic cell, a cubic unit cell. So the intercept, the unit intercept made by this backside face on the x-axis will be -1. And similar to this front face, the backside face is also parallel to y-axis and parallel to the z-axis. So the remaining 2 intercepts will be infinity. Thus, the 2 Weiss indices for the 2 planes are 1, infinity, infinity, and -1, infinity, infinity. Now we can convert this Weiss indices into Miller indices by just taking the reciprocal of these coefficient of intercepts. Right, so for 1, the reciprocal will be 1, for infinity it will be 0, and for this it will be 0. So the Miller indices for the front face is 1, 0, 0, while for the back side face it will be 1 bar 0 0. Now 1 bar, why we are writing 1 bar here? According to the sign conventions, according to the conventions of notations that is to be used in crystallography, a negative intercept in Weiss indices has to be written as a bar. Say if it is -2, then we have to write it as 2 bar. If it is -1, we'll write it as 1 bar. If it is -3, then we write it as 3 bar. So like that. In Miller indices, the negative intercepts converted to reciprocal are shown in the form of the number with a bar representation. Similarly, coming to the next face, next set of opposite faces, that is the yellow face over here. Clearly the yellow face is having an intercept on the y-axis, while it is parallel to the z-axis and to the x-axis as well. Similar is the case with its opposite face also. Now, this yellow face with its intercept on the y-axis alone will have the set of Weiss parameters as infinity, 1, infinity. Infinity for the x-intercept and infinity for the z-intercept, because there is no intercept at all. The plane is running parallel to both the axes, but it is making a unit intercept on the y-axis. So the y-indices for this plane, for this face of the cube, will be represented as infinity, 1, infinity. Similarly, for the face opposite to this yellow face, we can write it as infinity, minus 1, infinity, because it is lying along the negative y coordinate. Converting those y-indices to Miller indices, we can have, for this yellow face, we have 0, 1, 0 as the Miller indices, and for its opposite face, we'll have 0, 1 bar, 0. 1 bar again for the negative intercept, we write it as 1 bar. Coming to the third set of faces of the cube, that is the green face on top. Clearly, the top face is making an intercept on the z-axis alone and is running parallel to the x-axis as well as the y-axis. Hence, the two intercepts for x and y-axis will be infinity, and the same will go with the opposite face also. But for the y, there will be a unit intercept. So the y-indices for this green face on top will be infinity, infinity, 1. And for this bottom face on its opposite will be infinity, infinity, and minus 1, because the intercept for the bottom face will be on the negative z coordinate. Converting these y-indices to Miller indices, we have 0, 0, 1 as the Miller indices for the top plane, while 0, 0, 1 bar for the bottom plane. So these are the 6 Miller indices for the 6 faces of a cube. The last topic in this part is the interplanar spacing in a crystal system using Miller indices. This is one of the most important applications of Miller indices. Miller indices, as you know, were represented by HKL in small brackets of parentheses. HKL are the set of integers that we have used for defining any crystal plane, depending upon its intercept on the x, y, and z axis. And this has been, we have studied this so far. So the distance between two HKL planes, say suppose the distance between two 100 planes. How do we get the distance between the two 100 planes? Similarly, the distance between two HKL planes in general inside a crystal system can be calculated using the formula 1 by DHKL whole square is equal to h by a square plus k by b square plus 1 by c square. Now, where A, B, and C, what are these? These are the unit cell dimensions. H, K, and L are the Miller indices. So HKL we already know because the plane has already been defined. So the values of H, K, and L are very much known to us. We have to find DHKL. Now, if we simplify this equation for a cubic unit cell or a cubic system, for which we know that the edge dimensions are equal because all the edges of a cube are equal. So A equals to B equals to C. So this entire equation can be simplified and reduced to this formula. DHKL is equal to A by under root H square plus K square plus L square. Simplified, we just need to put the value for the edge length of the unit cell A, and H, K, and L are already known because the plane will already be defined, in the question. So you know the values of H, K, and L. You will be given the value for the edge dimension A. You just have to find DHKL. Say for example, let us calculate the interplanar spacing between two 2 to 1 planes of a cubic lattice of length 4.5 angstrom. See, the edge length has been already given. The 4.5 angstrom is the value for A, and 2 to 1 represents the Miller indices for this plane. So there will be two 2 to 1 planes, and you have to find out the distance between these two planes inside the cubic lattice. So for that, we'll just put the values in this formula and we get the value. So this is how Miller indices can be used to find out the interplanar spacing in a crystal system.